Testing, can you hear me? Testing, can you hear me? Hello. So I'm going to be learning RISC-V. Well, I'm going to be learning about computer architecture, but I will just be learning from where I last left off. Wait, hold on. So the last stream was on x86. This stream will be on RISC-V. So it's this book again. Last stream I learned x86, and now I'm going to be learning about RISC-V. Also, I found a RISC-V simulator online. I don't know how close it is to what they're going to teach, but I hope it's pretty close enough. Okay. How much should I zoom in? I think this is good enough. 36 pages. Okay. In this chapter, we will introduce the RISC-V assembly language, which is newer than ARM and x86. The ISA has a very interesting history. There are both legal and technical reasons for designing a new RISC ISA as late as 2010. Recall that ISA design was considered to be a dead area long before. Furthermore, a massive SWHW ecosystem is needed to sustain an ISA. What is SWHW? Which is hard to design from scratch. Nevertheless, there was a requirement in 2010 for a RISC ISA that could be freely used by everybody and incorporated a lot of the technical know-how that had been generated in the past 2 decades of computer architecture research. Okay. Any modern ISA should be compatible with all kinds of devices, starting from IoT devices to mobile phones to laptops to servers. Many of these devices didn't exist when conventional ISS were designed. This means that it should have 32, 64, and 128-bit variants, support a relatively large number of registers, and have extensive support for atomics and floating point numbers. Let us understand the situation that prevailed in 2010. Designing a simple RISC processor had become relatively very easy. The architectures were well understood, EDA tools were reasonably mature, and enough computational power was available to even amateur designers. Hence, putting together a small RISC core became feasible for fabulous companies and academic groups. It is important to note that circa 2010, there was a widespread consensus that RISC is a way to go for new cores, and x86 like RISC ISA were not an option. This is because of the 1000 plus instructions in RISC ISAs and the resulting decoding complexity. Decoders are power hungry, and given that these ISAs were meant to run on low power embedded systems, a RISC ISA was not a feasible option. However, just designing a RISC processor is not enough. It needs to be fabricated as well. A lot of chip fabrication companies, fabs, increased their capacity at that time, and it also became possible to design reasonably high performance chips at older technology nodes. Hence, fabrication became quite inexpensive. Along with these technology level tailwinds, many fabless companies rapidly came up in different parts of the world. They either wanted to design their bespoke processors or wanted to integrate their own custom cores with third-party accelerators in SoCs. They always had an option to use or modify existing RISC cores designed by ARM and MIPS, or design their own processors that are compatible with their ISAs. The advantage of using existing technologies is that their toolchain can be used. This includes the compilers, operating systems, libraries, and bin utils. Despite so much software support, many processor developers decided to forego the advantages of using existing ISAs primarily for legal reasons. There were a fair amount of restrictions and licensing requirements for using such legacy ISAs, while even designing new processors from scratch. Furthermore, licensing their cores and using them in SoCs were also proving to be an expensive proposition to many developers. There was thus a need to create a new ISA from scratch and also create the full ecosystem to support it. The idea was to have extremely lenient licensing requirements, such that the barrier to entry is reduced to a minimum. In 2010, the RISC-V project began in Berkeley. It was initially supported by various academic groups. Later on, the RISC-V technical documents were released under a Creative Commons license in 2015. Currently, the RISC-V Foundation maintains this ISA and publishes regular updates. Okay, so the machine model based ISAs and extension. RISC-V is actually not one instruction set, but it is a collection of instruction sets that incrementally build on top of each other. There are a set of baseline versions, common cores. Developers build on top of the common core by adding extensions. Given that the philosophy of RISC-V is to run on all kinds of machines, the notion of having a different cores ISA and extensions aligns with it well. Let us look at the common base ISAs and extensions in table 6.1. So the base version, we have RISC-V 32, 32E. 32E is the embedded version, 64, 64E, and then 128. Isn't there any 128E? E stands for embedded version. I stands for base integer. Wait, hold on. M, integer multiplication and division instructions. A, atomic instructions. F, single precision floating point. D is double precision floating point, and V is vector instructions. RISC-V has three basic versions, 32, 64, 128. Term RV is a short form, okay, of RISC-V. The numbers 32, 64, and 128 indicate the bit width respectively. The E suffix has a special place. It indicates the embedded version that uses a reduced number of registers. For example, RISC-V 32E assumes only 16 integer registers as opposed to 32 integer registers in the regular version. It is important to note that unlike other ISAs such as ARM Thumb, the instruction sizes remain the same. This simplifies compiler and processor design. Let us now focus on the extensions. Most versions of the ISAs support basic integer instructions. They are thus named RISC-V 32I, 64I, and 128I respectively. Okay. I want to see what the base instructions have. Like if you remove base integer. So just RISC-V 32, what does it contain? It doesn't contain any of these. It doesn't contain any multiplication or floating point or whatever. There are a bunch of extensions that can be added based on users' requirements. The list of extensions has become as large as 2024, around 20 to 30. No, as of 2024, around 20 to 30 extensions. Okay. Most of the common ones correspond to floating point instructions, atomic operations, cryptographic primitives, memory barriers, etc. For example, RISC-V 32 IMA means integer instructions. multiplication, division instructions, and atomic instructions are supported. Okay, I want to see what the base versions look like their instructions. These extensions themselves have a version numbers, a major version number, and a minor version number. This is because specifications keep changing as the ISAs are under development. For example, 32I1P3 means that the major version number is 1. The minor version is 3. The separator P is used to separate the major and minor version. So this version 1.3 belongs to just this I extension, right? Extensions can be grouped into packages the same way that we bundle together add-ons and flight and hotel deals. The G suffix that represents the general purpose computing combines the space integer instruction set, additional integer instructions, floating point instructions, and basic synchronization primitives. What does the G stand for? G is not shown here. What is the G? General purpose computing. So base integer, additional integer, base integer. So the G contains base integer ISA plus some additional ones. Floating point and basic synchronization primitives. This is considered to be an essential set of instructions in the multi-core setup. 32G is thus general purpose RISC-V ISA. It is so happening that the number of extensions is continuously increasing, and we are running out of letters. This is why the Z series was introduced, where the extension name should start with a Z and be followed by a word that describes the extension. For example, Z5 refers to additional floating point instructions. Let us now recall the fact that embedded version of RISC-V does not reduce the instruction width. It instead reduces the number of available registers by 50%. On the lines of ARM-Thumb, RISC-V does have a compressed format. In this case, the ISA specifier is C. Such context most often we use RISC-V 32C, general purpose and compressed. The compressed instructions have the following limitations. The width is 16 bits. Every compressed 16-bit instruction corresponds to a 32-bit RV32 instruction. They access a limited number of registers, typically limited to 8 registers in the 16-bit version. Limited opcode support, immediate values can be encoded are also commensurately smaller. I don't think I've ever seen this word before. Akin to any other compressed ISA, they lead to reduced code size, better usage of the iCache, and low power consumption in terms of fetching and decoding instructions. The greatness of RISC-V is that regardless of the width of the data path, the instruction size or width remains the same, 32 bits. This makes the process of compilation and decoding the instruction easy. The only thing that varies across the 3 different ISA formats is the set of support instructions, the register width, and the size of the memory address. So the instruction size is always 32 bits. And the register width is different. Size of memory address is different. Set of supported instructions. However, there can be some exceptions to this general rule. There are some RISC-V instructions whose size can be more than 32 bits. The restriction here is that the size needs to be a multiple of 16 bits. It cannot be an arbitrary size. I've already seen the save format instructions that are 16 bits in length. However, we can have longer formats, 48 and 64 bits. Such instructions are not part of the standard set of instructions, but there are extensions that require these longer instructions. Some of these extensions are vector instructions, uh, bit, bit manipulation instructions, and cryptographic extensions. The instruction format has bits to indicate if the instruction is longer than 32-bit or not. Current version of the standard uh, can theoretically support instruction lengths up to 176 bits. We need to note that at the moment, such extensions are in different stages of ratification. For example, there is a discussion of ratifying a more general set of 48 bits and 64-bit instructions. Similarly, the 128-bit format of the ISA is also not fully finalized yet. In other words, the standards are not fully frozen yet. Some debates during the course of ISA designs are very common. There is always a pull between the RISC-V and the CISC sides. The RISC side wants clarity and elegance, whereas the CISC side wants more instructions and more complexity. The RISC-V ISA is a RISC ISA. It is, however, not small and simple like simple RISC. Instead, it has a base set of instructions, a set of extensions, 48 and 64-bit instruction lengths, and different ISA variants, including a compressed 16-bit form. This sounds more like CISC. However, there is still a lot of regularity in ISA. There are few instruction formats. Instructions are mostly 32 bits in length. The base ISA is very RISC-like. Such trade-offs are inevitable in designing any modern ISA that needs to support a wide range of devices, embedded processors to supercomputer. RISC-V 32i contains 32 registers that are each 32-bit wide. The registers are named X0 to X31. X0 is hardwired to 0. Table 6.2. Wait. Okay, RISC-V registers and their assembler mnemonics. We are only talking about RISC-V 32i, right? I is base integer ISA. So then what is this? This what I found online. Which one is this then? There is a dedicated PC register that exposes the program counter. The architecture per se does not define a fixed calling convention. However, over time, a convention has emerged and developers are mostly using the calling convention shown in table 6.2. Note that the safe registers are preserved across function calls, whereas temporary registers are not preserved. RISC-V uses standard memory addressing model. It started out being a little endian ISA, but now big endian and bi endian modes are also supported. So 0, hardwired to 0, return address, stack pointer, global pointer, thread pointer, temporary registers, save registers, frame pointer. Given the machine model, let us now explain the instructions supported by RISC-V 32i ISA. Note that this is the fourth chapter on low-level assembly language, hence the treatment will be brief. Okay, so we have return address, stack pointer, global pointer. What is TP? Thread pointer and temporary registers. Thread pointer 0, 1, 2. Temporary. How many temporary registers do we have? While describing the semantics of instructions, we use the same convention as ARM and simple RISC. Okay, so the RS1 is the source, RS2 is the second source, RD is the destination, M is the immediate value. In some cases, there's a third source register. So moving values to register, add, and add I. Add and add integer. So what is this T over here? Thread pointer, what is T0, T1, T? So what version is this website using? Performance analysis, data path. T0, T1, T2 is temporary registers. S0 is saved register. S1 is saved register. A0, A1 is function arguments and return values. A2 to A7. A2 to A7. The function arguments. 2 to 11 is save registers again. 3 to 6 is 10. Why is it formatted like this? The most basic operation in any assembly language is to load a value into a register. We typically transfer the contents from one register or from the immediate feed of the instruction of an instruction. We need a counterpart of the move instruction in RISC-V. Why do we need a counterpart? The relevant instructions are shown in table 6.3. Why couldn't we just call it move instead of add? Oh, x0 is permanently 0, right? So we can add with 0. We don't need to store 0 somewhere. Oh, I guess then we don't need a move, right? The add instruction can be used to load assigned 12-bit immediate to show to the destination register. In this case, its usage is somewhat unconventional. As the example shows, the immediate is added to the contents of x0, which is hardwired to 0. Effectively, the immediate gets transferred to the destination register. An advantage of such a mechanism is that we need not have a dedicated move instruction. The add instruction and its variants can be used to load immediates. Similarly, we can set the immediate to 0 and transfer the contents of the source register to the destination register. This simulates the regular register move instruction. Why can't we have an add instruction that adds 2 immediates? A major issue with add instruction is that immediate value that the immediate is limited to 12 bits. Loading a full 32-bit value thus requires several instructions. RISC-V therefore provides the LUI instruction that loads a 20-bit immediate into the upper 20 bits of a register. The immediate is effectively left shifted by 12 positions. So load upper integer. Semantics of this instruction is shown in table 6.4. So load unsigned integer. Then what's the difference between the two? Example 91. Write a RISC-V assembly program that to add 409932 plus 409823. How do I write a comment? Is this a comment? What is, okay. Add I to, wait, I'm not looking at the answer right now. It's temporary register T0. T0. Let me see the example T0 X0. Okay, that worked. What does this do? Reset simulation. How do I delete all of this? Assemble 15. Assemble. And then what is this? Single step. Step back. Start simulation. Single step. And then 6 9 goes here. Okay, so they want this, right? But I can't write the whole thing there. Can I? It only works with 12 bits, right? Immediate must be between these two. If it only works with 12 bits, then they said I have to load unsigned load I. Okay, let's try load I. Load I to T0. Assemble. How do I delete? Can I have it in decimal? Okay, 409660. That's not what I did. T0 run code again. Or 09932. Okay, now let's do the same to T1. I need to make sure I'm doing it right. T stands for temporary registers, right? So I'm gonna use all the T registers. I don't know if that's the correct way. And guess 2 seconds is better. No. It wait like this much time. Okay, so anyways, we have T0, make this T1, assemble. Okay, now add to T2 what's stored in T0 and in T1. Let's see if that's what they did. What's this sum anyways? This seems like a correct answer. What's wrong with my answer? So they loaded this in first. Wait, I don't understand why they're doing this. So load upper integer. What it does is it loads the integer and shifts it by 12 positions. If you load upper integer 100, let's try that. Load upper integer to T0. 100, what do I get? Or what was that? Doesn't it need to shift? Hold on. Load integer. Load 0. 49600. Okay, so this is what I end up getting. Right. So if I put in 100 and then I shift it like 12 bits, what I end up getting is 409600. I see. But why are they doing it like this? It is evident from example 91 that loading a 32-bit value into register requires two integer instructions. Even though the ISA has this limitation, most RISC-V assemblers support the assembler directive LI that loads a 32-bit value into a register. The assembler replaces the directive with two assembly instructions ADI and LUI. Code in example 91 can be compressed using the LI assembler directive. This is what I did. Also, the LI instruction. Wait, my internet is fluctuating. So the LI instruction is a short form of these two, right? Add and subtract instructions. Add and add we have seen, and then subtract. Source 1 minus source 2. 6.5 shows the general form. They have a same general format as simple RISC, add and subtract instructions respectively. Instruction RD S1, S2. Okay. To compute 4 plus 5 minus 19. To swap two numbers. Store in x1 and x2. Just x1 and x2 again. RA and R. Is that even safe? So x3 has what x1 has. X1 has what x2 has. X2 has what x3 has. Okay. Table 6.6 shows the multiplication and division instructions. They're part of the M extension. The reason for including them in an extension is to enable the creation of really low and low power implementations that do not require such instructions. The multiplication instruction has some complications. The product requires 64 bits, which means that it will not fit in a single register. The default implementation thus places the lower 32 bits in the destination register. However, sometimes there is a need to store the full 64-bit product. This will require two registers. The default mul instruction computes the lower 32 bits. The mul high and the mul high unsigned instruction can next be used to store the upper 32 bits assigned for signed times signed and unsigned times unsigned multiplication respectively. Even though we require two separate instructions now, microarchitectures can fuse them dynamically. They can identify two consecutive multiplication instructions where one instruction computes the lower 32 bit, the next instruction computes the upper 32 bit. This sequence can be identified dynamically and a single multiplication will only be required. So multiply 3 with minus 17. Save the result in T3. Um, I don't know if you guys can see there's minus 51 written over here in T3. Or I don't even need T3 for this. Compute 12 cube plus 1 and save the result in T4. I am saving the result in T0. Just pretend that this is T4. Twelve cube plus 1, save the result. 12 cube. Hold on. And hold on. 12. No, wait. I'm loading 12. Then 12 times 12 is 12 square. And then 12 square times 12 square. Oh no, this is wrong. So add T1 x0. Or actually 1. And then in T3, you do 12 times 12. And then in T4, you do T3 12 square times 12. And then in T4, you take what's in T4 and add 1 to it. One 1,729. The division instruction. There, wait, I have a calculator. I'm just checking just in case. Yeah, it's correct. Div is comparatively simpler. In the RV32 variant, it requires 32-bit dividends and divisor. Quotient is stored in the destination register. The rounding is towards 0. Let us explain rounding using a few examples. So, division operation, quotient and remainder. Okay, we can see that, wait, we can see that rounding towards 0 also means that the sign of the remainder is the same as the sign of the dividend. The remainder instruction works on similar lines. It computes the remainder on the division operation. Akin to multiplication operations, the division and remainder operation work in a similar manner. When they are issued back to back, microarchitectures are expected to fuse them. They compute a single division operation and store the results in two registers, one register for the quotient, one for the remainder, respectively. This is an example of a scenario where the ISA has deliberately been under-designed. Instead of having an instruction that stores two 32-bit registers, programmer or compiler are expected to invoke these instructions consecutively. It is the job of the hardware to dynamically identify such sequences and fuse them. This transfers the responsibility of ensuring efficiency to hardware at the cost of keeping the ISA simple. Divide minus 50 by 3. Store the quotient in D2 and the remainder in D3. So 53 divide. Wait, where are the instructions? They didn't introduce the instructions to us. Okay, divide remainder. Logical and shift instructions. Oh, they said div. They introduced the div instruction, but where's the? Did they introduce the remainder one? Oh, they did. They introduced it here. The primary logical instructions are AND, OR, and XOR. We can attach I suffix to these instructions to accept an immediate value as the second source operand. And I, or I, XOR I. Shift left logical, shift right logical, shift with integer, shift right with integer. What is A again? Shift right arithmetic. Oh, it saves the sign, right? So it preserves the sign of the most significant bit, right? The format is otherwise the same as the old add and sub instructions. So bitwise OR of A and B, let A be 4 and B be 1. So you want bitwise OR of these two. I can just do it in 2 lines. Akin to other ISAs, RISC-V has 3 shift instructions: shift left logical, shift right logical, and shift right arithmetic. They have their values where the second source is an immediate. They are as, okay, yeah, I get it. Compute 50 divided by 4. Oh, you're dividing by 2 twice. So storing 50 here. Shift right integer. li. So taking t0 by 2, shifting it right twice, right? Okay, then you're dividing it. When you shift it right once, you're dividing it by 2. Wait. Shift right logical. Source immediate. 50. Requires 3 operands. Okay, okay. Wait, I have a calculator. Let me just make sure. It's 12.5, but the 0.5 goes away. So the 1, it like goes away, right? T2 plus T3 times 4. Um, Unlike simple RISC and ARM, X5 does not have a flags register that stores the result of the last comparison. The arguments for the comparison are typically specified directly in the branch instruction itself along with the branch target. Sometimes there is a need to store the result of a comparison. RISC-V thus provides a flexible mechanism to achieve this. It's conventional in RISC-V, the flags register is implicit, whereas it is more explicit in RISC-V. In the conventional RISC ISA, the flags register is implicit. Okay. Shift, wait, what? Set less than. So if less than, okay. If S1 is less than S2, then RD is set to 1. Set less than integer, set less than unsigned integer. Okay, set less than unsigned, it says set less than unsigned integer. Conditional branch instruction can then directly compare this register with 0, decide the outcome of the branch instruction taken or not taken. I like the way RISC-V is made, like how it's designed. Set T2 if 2 is less than 5. What? Set T2 is 2 is less than 5, okay. Gonna load 2. Set less than integer. No, not unsigned, just integer. Setting T2, T0, 5. 2 is less than 5 and that is true. Add okay, my internet is cutting out. Add 2 log 64-bit values stored in T1 and T0 and T3, T2. Store the result in T5, T4. Wait, 2 long 64-bit values, T1 and T0, and T3 and T2. T1 and T0 load I. So T1, T0 pair has 2 instructions. T1 has the upper bit. And then 3 and 2. 3 and 2. This is the upper value, right? Now we need to add them, but first add T0 and T2 and check if there is an overflow. We check if there is an overflow. How do we do that? Let's see. How is it doing this? T1. So what I'm thinking is adding T2 and T0. And if there is a carry, we add T1 and T3 along with the carry. So T4, it adds the lower 32 bits. T0 and T2, okay, that's what I said. Okay, let's first implement add T0, T2 and put it in T4. Those are the lower bits. And these are the upper bits. What about the carry? Sets less than unsigned. T4 is less than T0. Add the carry. So T5, T6. Yes, so you add 1 to T5. If T4 ends up being a negative number, that means there was an overflow. But wait, what? Don't we need to correct T4 as well? If there is an overflow, we end up with lesser than T0, right? Hold on, let me think on this. It discards the overflow, right? Okay, I think I understand. It discards the overflow and it keeps the lower 32 bits. But if there was an overflow, there will be one at the end, and the highest digit will have a one at the 1 at the start. And only other digits will be lower than T0 and T2 both, right? Otherwise, if it wasn't an overflow, then T4 should be higher than T0 and T2 both, right? Okay, that's how I understand, but I will have to check it off stream. Branch if equal, label, branch not equal, label, branch greater than, branch less than, branch greater than unsigned, branch less than unsigned. How does it work with negative numbers? Because the sign bit in the front, it's 1. But if we are just looking at the binaries, it will look like the negative is greater, right? Does it take that into consideration? Shouldn't the instructions have a signed modifier instead of unsigned modifier? The conditional branch instructions in RISC-V are shown in table 6.9. Instructions take 2 register arguments and compare them. The result of the comparison is immediately used to decide the direction of the branch. Recall that ARM has similar instructions. Okay, wait, I have to go somewhere. Just wait a minute. I'll be back in a few minutes. I am back. My voice might be kind of weird. I don't know, because I can't hear myself. Write a RISC-V assembly program that computes to compute the factorial of a positive number stored in A1. Save the result in A0. I have to remember this. I want to know how these registers are meant to be used. Factorial of a positive number stored in A1. Save the result in A0. Okay, I'm gonna load 5 in there. And end factorial. Result is stored in A0, right? Result is stored in A0, right? Save the result in A0. So we start with 1, we multiply 5, we multiply 5, we multiply um we are saving the result in A0, right? Multiply 5, and then we subtract integer. We subtract it by 1, so now 5 and then 4, and then we branch if it's not equal. Branch not equal. They're not equal, then go to end. Now that doesn't make sense. A0. Now branch, how do I do it with an integer? Can I do it with an integer? Branch greater than unsigned. Load into T0, 1, T0. So if it's not 1, then go to loop. How do you subtract with an integer? How do you do add I with a negative number? Yeah. Add I. I think 5 factorial is 120, right? 5 factorial is 120. Let's try. What is 15 factorial? Oh my god. 7. Let's try 8 factorial. A0 is over here. I just glitched for a second. What was that? Yeah, this answer is correct. Write an assembly program to add numbers from 1 to 10, store the result in S0. It's something similar to a factorial, but we are adding instead of multiplying. Test if a number stored in A1 is prime or not, save the Boolean result in A0. So we are going to assume that it is a prime, and wait, let me think about this. If it's a prime, then all numbers, all integers below it and above 1 should give a remainder, right? Yes, yes, yes. So it is a prime. We will assume that it's a prime. So load into T0. Oh, wait. T0, 0, A1. So you're putting 7 in there. We will test it with 7, 5, 4, 3, 2. 2 is the last one, right? Not 1. So you're going to divide it by every number and then subtract it. So this will be the next number. T0 will contain the number we're dividing it by. First it will be 7, then 6, then 5, 4, 3, 2, and then um branch if equal T1 x0 dot end. Sorry, my internet is fluctuating. So if the remainder is 0, then just go to end. Otherwise, it decrement T0. 7 becomes 6. And then go to loop. And it has to be above 2, right? that is not prime. So T0 is like 7654321. T0, we are decrementing it every time. And then need to check it if it's above 2. So if they're not equal, we go to the loop. If T0 hasn't reached 1, we go to the loop. Otherwise, if it has reached 1, then we go to end. It's probably a better way of doing this. Mm. So A0 is 0. That's correct. 7654321 divided by 7. Check the remainder when dividing it by 7. And if the remainder is 0, then mark not prime. Otherwise, we keep assuming it's prime. Decrement T0. So we can divide it again in the future. And check whether T0 is more than 1. It's more than 1. It's not 1, then continue the loop. If it is 1, then go to end. Okay, I'm satisfied with this. A0 is 1 when the input is 7. How about 31? Seven, 6, 5, 4, 3, 2, 1. A0 is 1. So let's see what they did. They seem to be. Wait, what's this? Jail. They introduced this before? What is jail? Okay, they did not introduce jail. Where is it? Okay, I never knew about jail. Unconditional branches. Okay, they're introducing it here. Unconditional branch jump instruction of RISC-V as shown. Table 6.10. The most commonly used instruction is JL. Jump to function label and store the return address in X1. Functions, both as a function call instruction as well as a regular unconditional jump instruction. In both cases, the control jumps to the PC pointed to by the label, akin to the other ISAs. While encoding the instruction, the label is translated to a PC relative offset. Jump can take place within a region of plus to minus 1 megabyte. The JL instruction additionally stores the return address in the first source register. Note that if the first source register is equal to X0, then the return address is not stored. JL in this case acts as a regular unconditional jump that does not store the return address. JALR, jump to address X2 plus 20 and store the return address on X1. The JLR instruction arguments, JL with one additional register argument. Consider the example JAL X1, X2, 20. In this case, we add the offset 20 to the contents of X2 and jump to the resulting address. Shouldn't this be JLR? Similar to JAL, we do not store the return address. The first register is X0. The JALR instruction can be used to implement a function return instruction. All that we have to do is to jump to the PC whose value is 0. 0 RA, or the contents of RA plus 0. This is the callee. This is the main. S0 to 3. Jump. RA is the return address. And then foo. 2 to A0. Jump to the return address, right? Return address is this instruction right here, right? Then add S1, S0, and SA. S0 and A0, right? Uh, table 6.11 show the load and store instructions in RISC-V. We only show the 32-bit versions of these instructions. The LW instruction loads a 32-bit value that loads 32-bit values from memory that is specified in the base offset format. On similar lines, the SW instruction stores the value of a register to memory. Note that the following store instruction takes two register operand. It has its separate format. Store instruction has always been an exception in such respects. RISC-V defines a special format for it, which accepts two register-based source operands and an immediate. Write an assembly program to load A0 with the contents of the memory address. SP minus S0 times 4 minus 12. So we make the memory address. We make the memory address T0 mem T0 in A0. So the memory SP plus 32. So 32 is the offset. And then we store it over here. Then what is LA again? What is LA? Forget it. Maybe they have an example. Write a RISC-V assembly program to compute the factorial of a number. Store in A1 using recursion. Store the result in A0. Add one. Oh, does it continue here? Elton. Return address. Factorial using recursion. Stack pointer minus 8. Okay, and then store the result, the return address in the stack pointer. Store in S0 4 times SP. And then make the recursive call. Go to factorial. And then once that is over, come to the return address. Okay, so you're going to loop into this function until we reach 1, in which case we will reach LT1, right? But when we are unwinding, when we are, what are we doing again? Factorial of a number. Factorial of a number. 5 times, where are we multiplying? Oh, we are multiplying here. Return address added to the stack pointer. Okay. The LA assembler directive. There's often a need to load values to memory before a program starts to execute. A need arises when we use built-in constants, and initialize global and static variables. Using the LI instruction, it is always possible to load 32 bits to a given memory address. However, it is possible to design a more elegant solution that in practice will translate to multiple assembly instructions, and it will nevertheless make the job of the assembly programmer much easier. The any directive achieves this. It is considered an example. Constant val needs to be defined as a label. Specific way of defining it is as follows. Val.word 17. A 32-bit integer constant requires the dot word directive, and a floating point constant requires the dot word directive. It is then succeeded by the value of the constant. The any directive can be used to load the address of a constant into a register. Subsequently, a regular load instruction can be used to read the value of the constant. So val.word 17. We have two choices, either dot word or dot float, right? And then we load a constant. So how do I pronounce this? LA load address of constant. Let us now look at the floating point instructions in RISC-V. In 2017, the FND extensions were introduced for a single precision, double precision floating point operations respectively. This part of the instruction set is quite conventional and is similar to other RISC ISAs. Floating point numbers are stored in the regular IEEE 754 format. The RISC-V floating point model has 32-bit floating point registers. Their names range from F0 to F31. Unlike integer registers, no register is hardwired to 0. There is, however, a register usage convention, akin to the integer register. Saved register. So these are for floating points, right? It's not possible to directly load an immediate into a floating point register. Like x86, floating point registers can only be initialized by loading values from memory. There is an additional special register called the floating point control and status register, whose structure is shown in figure 6.1. Its lower 8-bit encode important information. Okay. First 5 bits, starting from the least significant bit, stores exceptional conditions and counted since these bits were last reset. This is known as the F flags field. The rest of the 3 bits store the rounding mode. Accrued exception flags. Mnemonic and explanation. Invalid operation, divide by 0, overflow underscore inexact. The F flag feed stores 5 flags which are known as the accrued exception flags. First 4 flags, invalid operation, divide by 0, overflow, and underflow, have this standard meaning. Let's discuss the fifth that we have not encountered before. This is set when the result cannot be stored exactly in a floating point register and some rounding was required. Next, let us discuss the different rounding modes. They are stored in bits 6 to 8 of the FCSR, floating point control and status register. So R and E, round to nearest, prefer even LSBs, round towards 0, round down, round up, round to the nearest, prefer the number with the max IMA magnitude. Invalid, invalid. Selects a routing mode dynamically. What's the difference between these two? Round the 000 and 100. S5 instructions can use a static routing mode or a dynamic routing mode. The default routing mode is RNE. We round the result to the nearest value that can be presented in IEE 754 format. The real value is between two presentable values. The result is rounded to the value that has an even LSB. The next rounding mode is RTC, which is round towards 0. It's equivalent to truncation, where the bits that cannot fit in the format are simply removed. The next two rounding modes are self-evident, round towards minus infinity or floor, and the ceiling function. RMM is similar to RNE. However, if the result is between two representable values, then we round towards the number that has the higher magnitude. The next two values are not used at the moment. Finally, the DYN mode selects the routing mode dynamically. Prefer the number with the max IMA magnitude. You're going the one with the higher magnitude, right? Away from 0. Wait, with RNE, the RNE, if the real value is between two representable values, then the result is rounded to the value that has an even LSB. So, wait, lowest significant bit. Does that mean the last bit is 0? Or am I getting that wrong? Lowest LSB. Lowest, that has the lowest, that has an even LSB. I know. Okay. Let us now look at the basic floating point load and store instructions. They load and store values from memory, respectively. They do not perform type conversion. The FCVT instruction and its variants can be used to perform type conversions, as we shall see later. Key idea in RISC-V is the same as in x86, which is that floating point immediates cannot be directly loaded into registers. Their contents need to be stored in memory first, and then the 32-bit floating point value can be loaded into a floating point register. In this sense, this part of the ISA is less powerful than its integer counterpart. However, this does not cause much of a performance loss in practice, because most of the time we do not face the need for loading floating point immediates, other than while loading built-in constants such as pi and e. In this case, we can use the assembler pseudo instruction LA to store contents of the constants to memory and then load the address of the starting memory address to register. The floating point load and store instructions otherwise are quite similar to the integer counterpart in RISC-V. Yeah, I want to see an example. Load the value of a constant val into floating point register FS1. Load 3.14 A1. Wait, 3.14 is stored into A, but hold on. Aren't they supposed to store integers? And then load F, load W, float load float store W. FS10. Is there float values here? Wait, let me see if this works. We have value, we have main, we have, okay. It doesn't have the thing. I don't, why is A1 empty? Yeah, but float add, float subtract, multiply, divide, minimax, and square root. Wait, how do we take the square root? How is there a built-in square root? Table 6.15 shows the floating point arithmetic instructions. There of the form. There of the form. Instruction.s. Okay. The .s suffix corresponds to a single precision floating point instruction. The .t suffix corresponds to a double precision floating point instructions. Instructions add s, sub s, mul s, divide s, all have their usual meaning. Note that we do not have variants that accept immediates directly as source operands. In the case of floating point instructions, immediates can only be loaded using FLW instructions or converted from integers. Refer to example 116. Square root of this. Pi, we have e, load pi, and then that goes to fs1, load e, and that goes to fs2. And multiply, store it in ft2, and then square root at the end. I understand. I don't know how to code like floating points in here. Maybe if there's a way I'll find it. So what is this? Multiply and add at the same time, multiply and subtract. The multiplication happens first and then the subtract, right? Yes, I suppose if used arithmetic instructions used as the if used addition and subtraction operation. If used add instruction takes 3 register source operands as argument, it multiplies the first two and adds the product to the third. So F convert SW, F convert WS. So turn X5 to a float. And then this over here, turn float to X5. Convert the result to an integer and store the result in A0. .s.w, store it in T1, ft1. And load pi, load e, add 4 to the register. For ft1, they're storing 4.0. And then they're calculating pi dot times e plus 4. and then they're converting to an int over here. Comparing float point numbers is not the same as comparing integers. They cannot be directly given as arguments to conditional branch instructions. In this case, the statute of the comparison needs to be stored in an integer register. This register can then be compared with the zero register using a regular conditional branch instruction. If less than if L equal less than or equal, and then F equal over here. Okay. Arithmetic and data transfer instructions. RISC-V has four non-branch instruction formats: R, I, S, and U. There are These are for 32-bit instructions. RISC-V assemblers and compilers further align these instructions to 4-byte boundaries. Figure 6.2 shows a visual representation of these four formats. And table 6. Sorry, wait. Table 6.19 shows examples of instructions in each format. Hold on a minute. Um, so R structure is RD, source 1, source 2, source 1, source 2. What's this over here? Then RD, and then immediate type, opcode, RD, and then 12 bits for immediate. What is func3? S type, immediate. Okay, so for storing, right? Opcode, so an S to immediate, and then U type. Okay. Let's take a deep look at how each of these four instruction formats. First 7 bits are reserved for the opcodes in all the formats. This means that we can support a maximum 128 instructions in the ISA. Moreover, finding the opcode is also quite easy. First 7 bits. The reason that this is important is because minimizing the decoder's complexity is a key goal of ISA design. Given that all the opcode bits are in the same positions across the formats, finding the opcode and consequently the type of the instruction is easy. Wait, my My internet is fluctuating. I don't know why it randomly went to 0 kilobytes per second. It's working fine right now, but I think it will go back down again. Okay, I'm just near the end of the chapter, so I will just try to read what's left of it and then. Okay, it's going down again. Yeah, I will read whatever is left and then I will end the stream. Uh, the reason that this is important, okay, so the opcodes are 7 bits. Okay, I don't seem to understand what is happening. My internet is fluctuating up and down. Let me see if it goes back down again. If it does go back down, I'll just end the stream because I have been doing it for 2 hours. It doesn't seem to be going down. It does, then I will just end the stream. So the opcode is 7-bit. The reason that this is important is because minimizing the decoder's complexity is the key goal of the ISA design. Given that all the opcode bits are in the same position across the formats, finding the opcode and consequently the type of the instruction is easy. The next 5 bits are used to store the ID of the destination register in the RIU and U formats. S-type instructions do not have a destination register. For example, the SW instruction, which is an type instruction. It, however, has two source registers and an immediate. Instead of changing the positions of the source register in the S-type instruction format, the ISA designers have made the right decision to use the bits for the destination registers to store a part of the immediate. Hence, the first 5 bits of the immediate are stored in the corresponding positions. So the immediate is larger. Some of the bits are stored here. And there are 2 source register. What is this funct? I want to know that. Next, let us consider the U-type instructions. We can use the remaining 20 bits to store the 20-bit immediate. We don't need to store any more information. Such instructions have only 2 arguments, the destination register and the 20-bit immediate. The rest of the 3 formats store a 3-bit feed called funct3. It is used to hierarchically organize the instructions to also support more instructions. In RISC-V, a single opcode can correspond to multiple instructions. For example, the opcode at set less than and XOR instructions are the same. They're differentiated by the value of func3 field. Oh, I see. Opcode and func3 is like, it tells more about the opcode. The opcode is not, cannot store enough, right? And what is func7 then? However, that is not the main aim here. We can group similar instructions such that they are processed by the hardware in the same manner. We still have differences between them, such as add and XOR. However, most of the processing can remain the same given that both are R-type instructions. Next 5 bits store the S1 field in all three formats. Subsequently, differences arise. Okay. I-type instructions need to store a 12-bit immediate. They don't have a second source register. Thus, they use the remaining 12 bits to store the immediate. All immediates are sign extended before being used by hardware unless the instruction has a use suffix. The R and S type instructions store the second source register S2 in the next 5 bits. Let us now consider the last 7 bits in the R and S instruction. R-type instructions have another opcode extender called func7. Serve the same purpose as func3. The aim is to increase the number of instructions and also to create a grouping of instructions based on their similarity. It's possible for two instructions to have the same opcode and func3 fields, yet have different func7 field. Consider add and sub. They have the same opcode and the same func3. However, their func7 field are different. In contrast, S-type instructions store the remaining 7 immediate bits in the uppermost 7 positions. But that's for the immediate, right? That's for the immediate. S-type also has 12 bits for the immediate. Recall that we had already stored 5 immediate bits in the position at which other formats store the ID of the destination register. This is a very reasonable decision because the explicit aim is to ensure the same field is stored at the same set of positions across the formats. It is very easy for the decoder to extract it. Let us now look at the instruction formats for encoding control flow instructions. There are 2 formats in this space, the P and J formats. All the conditional instructions like B equal, B not equal, and B less than are implemented using the B format. Recall that such instructions take 2 source registers, they're compared, and then based on the results of the comparison, a taken or not taken decision is made. Instruction uses BC offset based in addressing where the offset is encoded in immediate field. So 7 bits for the opcode. What is this 12 over here? Immediate is this free bits? 7 plus 5 is 12 bits for the immediate. Func3, opcode and func3 together identifies the the instruction. Then we have the source, the second source. And then we have a 1, 1 over here. The immediate is encoded in a special manner in the B format. The offset needs to be a multiple of 2. This means that its least significant bit is 0. Given that this bit is fixed, there is no need to represent it. In other words, the 0th bit is set to 0 and thus need not be represented. Format thus stores the rest of the 4 bits in the first 5-bit field. Now that as compared to the S format, the immediate bits 4 to 1 are stored in exactly the same positions. This makes extracting these bits very easy, and there is consequently no need to design additional decoder hardware to handle these bits differently in the B format. Given that the 0th bit is not stored, its corresponding position can be used to store the 11th bit. The rest of the immediate bits are stored in the most significant bit position. Most significant 7 bits store the 12th bit and the bits 10.5. We thus store 13 immediate bits. 12 of them are explicitly stored and the least significant immediate bit is assumed to be 0. This format can thus encode an offset between minus 4096 and 4095. Plus and minus 4 KB. This offset is sign extended and added to the PC. Next, consider the J format. It takes a single destination register and a 20-bit immediate as its arguments. The immediate here encodes an offset that is a multiple of 2. There is no need to store the least significant bit, which is set to 0. Like the B format, there is a need to store 20 bits. The order of storing the bits from most significant position to the least significant position is as follows: 20, 10 to 1, 11, and then 19 to 12. Given that we encode 21 bits in this format, we can represent offset range that is within plus minus 1 megabyte the current PC. Over here, this this bit is set to 0 always, right? Positions to store the 11th bit. Hold on, let me think about this. Each significant bit is 0. Given that this bit is fixed, there is no need to represent it. Immediate bits 4 to 1 are stored in exactly the same positions. So the 11th bit is stored over here. 12th bit is stored over here. Start with this side. And this 20, why did they break it up like this? Why is the 11th bit and 20th bit? Can't they store the 0 over here at the start? in floating point instructions. Figure 6.4 shows the encoding of float load and float store instructions. Float load instructions are encoded in the I format. The funct3 instruction is replaced with the width field. Okay. Similarly, if store instruction is encoded using the S format, the only change is that the funct3 field is replaced with the width. Okay. 6.5 shows the encoding format of the floating point arithmetic instructions, variations of the R format. All such instructions take one floating point destination register and one or two source registers as inputs. The format is the same for all variants. The RM field encodes the routing mode and the FMT field represents the precision. The routing mode, precision. Then funct5, what does funct5 do? The opcode field is typically the same for all common floating point arithmetic instructions. Funct5 field stores the code for the specific type of instruction. For instructions like f square root, they miss the square s, they miss the s, that do not have a second source register. S2 field is set to 0. Same format is also used by floating point conversion instructions. This format is also used by floating point comparison instructions. The RM field in this case stores the comparison conditions equal less than equal to. The funct5 field stores a code for floating point comparison, FCMP. Figure 6.6 shows the encoding format for fmadd and fmsub instructions. Instead of funct5, third source register R3 is stored in its place. The rest remains the same. FMT, what was FMT again? Represents the precision. Okay. Rounding mode and destination. Okay. I didn't think I would be able to finish, but I did. Before my internet fluctuates again, I will just quickly end the stream. And yeah, I will see you guys next time. Bye then. Wait, let me see what the next chapter is. Okay, the next chapter is about logic gates, register, and memories. Okay. Alright, I will end the stream here and yeah, I will see you guys next time. Bye.